4.7.1. This is about inverse functions. Now let me try to introduce this to you in a way that I think makes the most sense. If I said sine of 30 degrees is 1/2, then you know, have you got this one memorized yet? Okay, you know where I got it from a triangle, right? From the 30, 60, 90 triangle, and we know those sides. And okay, so then what would the inverse be? The inverse is where instead of knowing the angle and saying sine of 30 is equal to what, and then you figure out, oh, okay, so I have my triangle, and it's a 30, 60, 90, and 1, 2, square root of 3. Instead of doing it this way and finding the sides, what if instead they gave you the angle, or sorry, they gave you a theta for the angle and said the answer was 1/2. Now, you've seen this before, haven't you? Haven't we done ones like this? Okay, but we just never like showed you how you actually are solving this. Think of this as an equation. Do you get that in an equation you want to get the variable alone? So is the sine the thing we want to get rid of so that the theta will be alone? Yeah, want to get rid of sine somehow. Guess what gets rid of inverse sine? Just like, you know, if I was going to get rid of a 7x equals 14, I divide both sides by 7, right? So the opposite of times 7 is divide 7 on this kind of problem. So that gets x alone, right? Same idea. What gets theta alone? What gets rid of sine? Nope. Inverse sine. Inverse sine. And I know that everybody's first thought is, oh, you must be talking about the flipping sister, which would be cosecant, but it's not that. I'm going to pause for a second. Okay, so before we got interrupted by the group that came in, now I'm back to telling you how to use an inverse sine to solve this problem. I know you're thinking inverse sine is like one of those other functions. It's not. It's just sine with a little -1 on it. Inverse sine. If I take the inverse sine of this and the inverse sine of the other one, I'm going to move this 1/2 over, just moving it over to make room. I'm taking inverse sine on both sides. And that gets rid of sine. Inverse sine and sine cancel each other out. The answer is theta equals sine to the -1 of 1/2. Have you ever noticed that on your calculator? Grab a graphing calculator. Everybody take out your graphing calculator. Let's find inverse sine. I am taking a wild guess that it's right near the sine button. It is. If you don't have one of these, borrow one from me. Just make it fast. They're up here. Just leave me some collateral. And if you haven't been bringing your calculator, you might want to start bringing it again. Thank you. I have another one. Don't worry. Collateral? Yep, I do. That'll work. Thank you. Phone would be good. Thank you. You certainly don't need it anyways right now. Yes. Any USB charger works, but I don't think I have my cord. Thank you. I'll pause the recording for a sec. So we're looking for inverse sine. It's right above sine. So on your graphing calculator, look above the sine key. Do you see how it has a sign with a little -1 there? That does not mean cosecant. If it meant cosecant, it would say cosecant. It's not the same thing. What you use inverse sine for is, do you know that normally you type in sine of 30 on the calculator and it tells you the other thing? What if you know the answer is 1/2 and you want to know how many degrees? Then you do this. You do inverse sine. So let's do it. Type in inverse sine of 1/2, and you can abbreviate that by saying 0.5. It'd be fine. Inverse sine of 0.5 equals what? 30. Now, if some of you are not in degrees, if you're in radians, it's going to say your answer's like 0.52 because that's half of a radian. You know what I'm talking about? So everybody get into mode. If your answer didn't come out to 30, if it came out to 30, you're good. You're in degrees. If your answer came out like 0.5 something weird, that means you're in radians. Get into mode. Get yourself out of radian mode. Get yourself into degree mode. By the time you hit BC calculus, you might be able to do radians as your standard thing you're using on the calculator. But for now, you don't want to go there. All right, so now, if everybody's got this changed to degrees on their calculator, it should have come out to 30 degrees. All right, let's do some other ones that are fairly common. Again, do you remember in the 45, 45, 90? 1, 1, square root of 2, you remember that? Now, just from the triangle, I could do this problem, but I want you to think about it. If tangent of 45 would have come out to what? What's tangent of 45? Come on, what's tangent of 45? Opposite over adjacent, 1 over 1 is 1, right? If tangent of 45 is 1, let's verify that. Type in tangent 45 equals, and let's see, make sure you get what we're doing here. Tangent of 45, did it come out to be 1? If it didn't, you're not in degree mode. You're still in radian mode. Get it fixed. Okay. If that worked, then what are we doing today? We're doing inverse functions. So what could I do? I could do, to solve this, I would not have had the 45. They would have said tangent of what equals 1. And you would have said to yourself, oh, I need to get the theta alone. I'll take inverse tangent of both sides. And inverse tangent and tangent cancel each other out. Theta is inverse tan of 1. Everybody type in inverse tan of 1. It's the one right above tangent on your calculator. Did you get 45? You starting to see how this thing works? It's sort of like Jeopardy. They're telling you the answer to the question, and then you got to say the other one, like what was the question? All right, I'll give you another one. Let's say that the sine of something is 1 over the square root of 2. You would be able to then say inverse sine. Fixes that. That cancels that. Theta is inverse sine of 1 over square root of 2. What was it? 45. All right. And why? Because if you look at this picture, if sine was opposite over hypotenuse was 1 over square root of 2, it must have been in a 45 degree, 45, 45, 90. All right. So your questions are going to often be really simple. They'll say something like, tangent of something is 1. Nope, they actually will do all the work for you. They'll have already taken the inverse tan on both sides. And so what would the question be then? Tan to the negative 1 of what? Of 1. That's what the question will say. Inverse tangent of 1. Do you get what they're really saying is tangent of what angle is 1? Okay, so I want to get you good at rewriting these things. So what if it says sine of negative 1 square root of 3 over 2? Normally, that's where the angle goes. That's the point. This is rewritten. So I want you to be able to say, oh, so you mean sine of some angle is root 3 over 2. That's the first thing I recommend you do on all of these, is to rewrite them like we've been doing them up till now. See, you put the angle right here. Now you can tell, oh yeah, this is wanting me to tell the angle. And then you can type it in the calculator, would give you the answer. Or if they're numbers you already know, you wouldn't be using the calculator. So in other words, like this one, as soon as I've rewritten it like this, do you get that's just a triangle where the opposite side is square root of 3 and the hypotenuse side is 2, and therefore this must be 1, and therefore how many degrees is it? No calculator needed. This must be the 60, because across from the 1 is where the 30 is. You know what I'm talking about? They're across from each other. And therefore this angle here must be the 60. So the answer is 60. Could you say that in radians? Sure. Pi over what? Pi over 3. All right. So let's do another one. Inverse cosine is root 3 over 2. Inverse cosine of root 3 over 2. I said it wrong. So first thing, I'd want you to rewrite. Everybody, please rewrite this thing as a function problem with the theta in it. Turn it my way. I'll tell you if you did it right. That's it. Now make the triangle and solve it. That's it. Now make the triangle and solve it. Did you've done too much? Just the rewrite. Cosine of theta is yes. 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 Yes, that's what I was looking for. Now actually finish it if you got the yes from me. That means you did it right so far. Good. 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 Okay. This is so critical. I mean, I know yes. I know that most of you are getting it, but I needed you to show me. Because if you don't get this, you really don't know what you're doing. Cosine of theta is root 3 over 2. That's what you're really doing. Now you're figuring out an angle. And now hopefully you drew me a triangle. And then you went, okay, cosine's adjacent over hypotenuse, adjacent square root of 3, hypotenuse 2. This must be a 1. What's the answer then? 30. Or in radians, pi over 6. That's the answer. Do you get how these things are reversed? The angle used to always be right next to the function. When you are doing inverses, they are reversed. Okay. That's the main meat of the lesson for today. But there's one more topic that we got to get through. And that is, what does this look like in a graph? Okay. Do you remember how we had inverses? Do you remember how we had a 3-step process to building an inverse? You'd like change the f of x to a y, and then the y and the x get reversed. Do you remember that whole thing? Well, this is inverses again, except it's inverses in trig. Okay, so let's see if you can hang with this. If this is my graph, looks like an exponential graph, kind of exponential growth kind of a thing. Okay, if this is my graph, and this is the line y equals x, an inverse is the flip of this line across that dotted line. Can you see where it would go? The other thing to think is that x's become y's and y's become x's. Okay, I can just see this. To me, I see that. Can you see that too? That's how you reflect that. This is important. Now, if you can't see that, you have to be able to handle it a different way. And would you agree that that spot could be sort of like 8, 1? Do you get how that's kind of like 8, 1? Then take a wild guess what's on the inverse. If 8, 1 is on the green graph, what's on the inverse of it? 1, 8. Do you get that? So if you're having trouble reflecting one, which all of you will, these are hard spatially. And sometimes some of you know, like when the teacher says to draw a 3-dimensional box and you're like, I can't, I'm terrible at spatial stuff. This thing will bother you. So you got to have another way. So if this is over 8 and up 1, then I go over 1 and up 8. See what I mean? This point and this point are inverses of each other because this would be like 1, 8. So you pick another spot. Imagine, I can use imaginary numbers. Let's say this is 12, 4 right there. Then what would have to be on the other one? 4, 12. Over 4 up 12. Like there. See what I mean? You could create the inverses based on knowing that the x's and the y's are getting reversed. Why do we care? Because when you are doing a graph of inverse sine, you are going to have to be able to say, okay, what's sine look like? Everybody, start with a sketch of sine, please. If we have to do inverse sine, we have to do a flip of this graph. And do you agree that this graph keeps going? I mean, it just keeps going forever, right? We don't want to do an inverse forever. So we limit ourselves and we say we're only going to do our inverse in a certain place. Okay? So I want you to sketch sine back the other way a little ways. Go back across the y-axis. Now, would you agree this area that I'm leaving up on the board is part of the sine graph? I just erased a different part than we normally start at the origin and go from there. Would you agree this is still a sine graph? How about if I erase even more? Would you agree it's still the sine graph, but it's just part of it? Okay. That's part of the sine graph. Now, if I want to do a flip across the line y equals x, because all I've graphed so far is y equals sine of x. I just limited it to part of it. You know why I limited it to part of it? Do you remember there's so many things in precalc that build on each other? And remember, we're getting into the tougher part of trig here, so you need your full brain with me. Some of you are drifting a little bit. I know. It's been a long lesson, so stay with me. Do you remember that there's the vertical line test, but there was also the horizontal line test? By cutting this sine graph down to what I did, it now passes both the vertical line test, which was like when you run a line over it like this, it never crosses more than once. You know what I'm talking about? It passes that version, and it also passes the other version, which is like this, the horizontal line test. In case you forgot the horizontal line test, which this would have failed when it had this tail on it going like this, see, it would have touched twice. So we have to narrow this down to only the part of sine that can have an inverse. The part that passes the vertical and horizontal line tests, that was called a one-to-one function. And between here and here is the only place it works, and that's from pi over 2 to, take a guess if there's symmetry here, negative pi over 2. All right, that's your graph of sine. All I've done is narrow down your graph of sine to the part of sine that actually can have an inverse. Now, the inverse is the flip across the line y equals x. So let's figure out where the line y equals x is. I'll draw it with a green dotted line, like that. There's approximately the line y equals x. So now, can you in your head flip this thing over? I can. I hope you can. Flipping it across the line. Flipping it across the line. The red graph is the graph of inverse sine. Now, if you want to, you can just memorize what that looks like. But it's important for you to understand where it comes from. That the x's become the y's and the y's become the x's. Remember that strategy I was saying before? Like we could say this is over 3 comma up 5 in the original. And so then this spot would be like over 5 up 3. Anyway, each of the x's and y's have been reversed. All right, so what did we just draw there? The blue one was sine and the red one was inverse sine. So that's the graph of inverse sine. They're just going to ask you in the homework, graph inverse sine. There you go. Have good notes and then it'll be no big deal. All right. And now, one last thought. Do you remember how the domain and range of the original, of sine used to go from 1, the blue one here, to -1. If my x's and y's got reversed, then that means that these blue ones aren't here anymore. Pi over 2 and the negative pi over 2, they're not there anymore. They're here now. Why? Because y's become x's and x's become y's. What used to be on the y-axis now is on the x. What used to be on the x-axis now is on the y. And then what used to be the height, you know, when we were going from the highest to the lowest, they used to be a -1 to a 1. They're here now. And the original one, the blue one, is now gone. It's in the junk pile over here. And your final answer for what is the graph of inverse sine is that. That's the graph of inverse sine. And that's why it is the way it is. I could have just slapped it up there and said this is inverse sine. But I needed to show you where it came from. And frankly, when you forget, because you will forget, there's a whole bunch of them I got to show you. When you forget which one's inverse sine, which one's inverse cosine, what do they look like, you can always just recreate them by graphing original cosine and flipping it across that line. In this case, I did sine. So next I'm going to do inverse cosine. So we'll do it a lot faster. All right, here's regular cosine. Everybody draw me a regular cosine graph. Remember how it looks kind of like a valley? This is 2 pi, blah, blah, blah. Would this whole thing pass the vertical line test? Vertical line test? Yes. Would this whole thing pass the horizontal line test? No, it fails. So I got to erase part of it. Can you see in your head which part I'm going to erase? From pi on, you were right. Do you get how that part of cosine passes the vertical line test and the horizontal line test? And so that's the part that we're going to flip. We're going to do the switch-o, change-o. Now what is it normally? It's from 0 to, it was halfway through its cycle, so from 0 to pi. And how high does it normally go? 1 to -1. That's the reason we're only using this part of cosine, is because it'll pass the vertical and horizontal line tests. Now, what I have to do, if you had forgotten what the inverse cosine graph looks like, you'd want to now take it and flip it across this line, y equals x. This one's harder to see, like where it's going. If you want to try to freehand it, it's not going to be very easy. So do you remember that little task I was giving you before? This spot right here is 0, 1. Would you agree that that's 0, 1? Then what has to be on the inverse? 1, 0. So I'm going to put a dot right about here. Okay. Then this spot is kind of like 1, 1, and so therefore its reflection will also be on the graph, which will be 1, 1. So do you get it's kind of curving up like this? Now another spot that's on the graph. Let's say this spot here is at like, I don't know, like almost halfway to pi, but do you get that this spot has to also be recreated in the inverse? So the original got flipped down to here. Okay, it's already over here. I'm sorry. I already had done that here. This got flipped to there. This spot here on the red one doesn't change because it's right on the line. Okay. So I'm going to put a blue dot right there. Okay. Now how about a spot like this? Where is this spot on the red one? Well, it's like 3/4 of the way over, and I'm going to call it something. I'm going to call it like, isn't it kind of like 8, -4? So then that would be kind of like, no, yeah, that'd be kind of like negative 4 comma 8, which is like way up here. And now there's your graph of inverse cosine, the green one. Okay, so if I needed to label it, I'm going to draw a new one now. It used to go from 0 to pi. So now that means this is from pi to 0. And it used to go as high as 1 and as low as negative 1. So it still goes from negative 1 to 1. It's just that my 0 pi and my 1 negative 1 got reversed. There's my graph of cosine. All right, one more. Take a wild guess which one. Sine, cosine, tangent. Okay, so let's sketch tangent. The beautiful part about tangent, remember how tangent looks? It was always rising like this. Does it pass the vertical line test right now? Does it pass the horizontal line test right now? Cool, then we don't have to do that weird limiting it thing. We just have to take this and flip it over the line y equals x. It goes from pi over 2 to negative pi over 2. So now we just got to flip it across that line. So what's the line look like? That's the line y equals x. So when I flip it across that line, do you get how it's kind of like if you turn your head sideways, it kind of looks like cotangent running the other way? Can it cross those asymptotes? No, but it doesn't have to, because you remember how those get reversed? Everything gets reversed. So here's your new graph. The asymptotes now go this way. And those asymptotes were at pi over 2 and negative pi over 2. All right. This is a positive pi over 2 here. It's just like in the middle of the asymptote line. Then it's running this way. There's your graph of inverse tangent. Now, we could give it a token label of a 1 and a negative 1 here, although we've never really cared much about where exactly they were. Now, if you feel like your mind kind of exploded there, don't feel bad. The graphs of this is a very small part of the big picture. Let's do some of the problems together now. So, everybody get to, now you want these notes, believe me. When they ask you later to write down the graph of inverse tangent, you're probably going to want to have your nice clean little picture here to be able to put that in, because you don't have a textbook per se that's going to tell you that. You could look it up. I mean, I guarantee you can Google what is the graph of inverse tangent, and there'll be some picture. It'll be pop up in 5 seconds. Okay, but these you're not going to be able to Google on the test, right? So I created all of these by knowing what tangent looked like and flipping it across the line y equals x. That dotted diagonal line, this line right here. So if you know where that dotted diagonal line is today, you can just take all your graphs that you used to know and flip them across that line. All right, this is 4.7.1, right? Everybody find the worksheet for 4.7.1. I'm going to pause while I get that up on the screen. I really don't want here to just graph these for you. You either have to look back at your notes and get them, or you're going to have to recreate them by knowing, what I'll give you is, here's the part of sine. This is part of our sine graph that we flip, okay? You'll have to do the flipping. And then remember, whatever used to be on my y-axis labels, they get reversed and they become my x-axis labels. And that tells me my domain and range. My domain is whatever the range of sine used to be, and my range is whatever the domain of sine used to be. Get what I mean? If you know domain and range of sine during this little interval here, from negative pi over 2 to pi over 2, if you know that's domain, which is what I just said, then you can reverse it, and that's the range. Does it touch? Yes. Brackets. The domain is whatever the range of sine used to be, which you should know. Can't picture sine. Here's sine. Hopefully you know what the range was, how high to how low. Okay. I need you to think these through. If I just do them all, then you haven't done your homework. I've done your homework. Okay, so 1, 2, and 3 are ones we definitely want to leave in there. And you can get from your notes that I gave you today, if you have notes that you should have had. Okay, find the exact value in radians. So basically, we don't want you to use calculators for this part. Remember me starting the hour with this? My first thought on this kind was, say, sine of some angle is √3 over 2. That's a rewrite. I call that a rewrite. To me, that makes the problem a lot easier. Now I realize, oh, all I want is an angle. And then I can draw my little picture. If sine of some angle, sine is opposite over hypotenuse, square root of 3, hypotenuse is 2. So all I really need is the angle, and the angle there must be, let me think, the one that's across from the square root of 3 is the 30, 60, 90. Which one is it? 60. Good, but then what radians is 60? Pi over 3. There we go. Arc cosine, what in the heck is that? Take a wild guess. What do you think it means? Inverse. It means the same thing as inverse cosine. Just another way to say it. I think it's because in the old days, it was hard for them on a typewriter to put in a -1. In fact, I've read this somewhere, so I think I'm 98% sure it's right. That the reason they say arc cosine is just it was easier to type than cosine with the little -1 exponent. Okay, so arc cosine means the exact same thing as inverse cosine. So it's exactly as if they had just said cosine -1 of √3 over 2. And a rewrite would be cosine of some angle is √3 over 2. So it's just like this previous problem, it's just cosine instead of sine. So now I draw my little picture and I go cosine adjacent over hypotenuse, little helper monkeys in there. On the adjacent side, square root of 3 to my angle, which is here. And my hypotenuse side is 2. And then that must mean this is a 1. And what's across from the 1? It's a 30. And therefore, what is this one? 30 is correct, but also known as pi over 6. Yeah. All right. So none to skip yet because they've been all critical. Like, you got to know these to be able to handle. Sorry, I hit the wrong button there. Clear ink. There we go. But there's a little much in here. So I'd say, why don't you skip 16, 17, 18, 19. 16, 17, 18, 19 ought to be fine. You may skip 16 through 19. There's 4 questions at least. I do want you to do these last couple because you need some that have a negative in them. In case you're wondering about that, all that means is your triangle is drawn where sine is negative. So you're saying to yourself, sine of some angle is negative square root of 3 over 2. I want to help you with 20 though, because a lot of people get messed up by this one. Where is sine negative? Well, all students take calc. Right? So where's sine negative? Well, sine's positive here and here, so it can't be there. So a lot of people think, so there's 2 answers. One's over here, and one's over here. Wrong. Why? Because, do you remember that for sine, it only had an inverse between negative pi over 2 and pi over 2? Do you get that this angle right here is not between? In this kind of a picture, that's where pi over 2 is. In this kind of a picture, that's where negative pi over 2 is. So it can't be over here. Inverse sines only work between negative pi over 2 and pi over 2. Because otherwise it won't pass the horizontal line test. So, last thing I want to give you is a picture. And I will tell you today, and then I'll reinforce it on Monday, so that hopefully it sticks between those 2 times. Here's the picture that you need to get about where things are allowed. And this will help on the more complicated questions. Inverse sine only works from here to here. Inverse cosine, do you remember that one worked between 0 and pi? You know, when I had the little picture of it, it was okay from there to there. That was cosine, and it stopped working there. That was between 0 and pi. So here's cosine. Inverse cosine only works in here. And inverse tangent is the exact same thing as inverse sine. At least there's something simple. Inverse tan this green one here. Inverse tangent only goes between pi over 2 and negative pi over 2 also. So, do you get this quadrant right here never works for any of them? That would be handy to remember. You're never going to be in quadrant 3. If you're ever drawing your triangle over there, you're doing something wrong. And what if they have you drawing a triangle here and then finding sine of it? Won't work. Because sine only goes in quadrants 1 and 4. Or if you're talking ASTC language, that would be sine only works in the A and the C areas. So if they were asking you to do a sine problem and you thought you're supposed to be over here, you're not. You won't be doing sine over here. What could you do over here? What would work over here? Inverse cosine could work over there. But that's the only thing that could work over there. And what one quadrant works for everything? That one. Still the best of all quadrants. Because all of them work there. Okay. So this little picture, I'm going to clean it up now for you, is like if you could have this on your tests, which you can't, but if you could, it would be a huge advantage on this next test to know where you can be for each of these things. Because a lot of times kids give an answer and they think like, okay, my inverse sine answer is going to come out to something over here. Nothing works over there. Or my inverse sine answer comes out to be like 3 pi over 4, which is over here. Inverse sine can't be over there. So you'll understand better about why that's so important later. Okay. You learned a lot today. Heavy duty pre-calc day. Now, I have only a few seconds. I'm going to show you your test scores. If you want to have some serious time with them, you can ask me for them again on Monday. That's all I have for the video for today.